All right, so when you perform simulations, just keep in mind that what simulations are we're basically looking at some sort of probability, and then we are going to simulate that using random numbers in order to see if that probability is in fact true. All right, so just a couple things. I'm going to be showing you some examples to look out for. Number one, make sure that during the plan section, you clearly communicate the method that you're going to use to perform the simulation. So you're basically restating what the probability is asking. Remember that all of the labels have to be the same length. So when we're doing this, make sure you use, if you're doing 1 to 100, the label should be 001 to 100 because they're all 3 digits, okay? If you're sampling without replacement, make sure to clearly state that you're going to ignore or skip repeats. We'll talk about this in a minute. When do you ignore repeats? When do you not ignore repeats? Make sure that when you're describing your simulation, you should be able to hand your description over to someone else, and they should be able to get the exact same results you did. If they don't get the exact same results you did, then you better start thinking about something and seeing what you did wrong. So just remember, what you're doing is you're using a calculator to model a situation to see if you get the same probability that's in question. All right, so let's just take a look at an example. So remember, I used to buy boxes of cereal, see what was in the bottom. I used to buy them and just eat them to see what toy was at the bottom. Or you go to McDonald's or Burger King and you dig through, you say they're all the Star Wars characters, so you kept going back until you got all the Star Wars characters, or the Beanie Babies. Okay, the mini Beanie Babies, I remember in the Happy Meals, I kept going back till I got all the Beanie Babies. So in an attempt to increase sales, this is a similar situation. A breakfast cereal company decides to offer a NASCAR promotion. Each box of cereal will contain a collectible card featuring one of these NASCAR drivers: Jeff Gordon, Dale Earnhardt Jr., Tony Stewart, Danica Patrick, or Jimmy Johnson. The company says that each of the 5 cards is equally likely to appear in any box of cereal. So NASCAR fan decides to keep buying boxes until she has all 5 drivers' cards. She's surprised that it takes her 23 boxes to get the full set of cards. Should she be surprised? So the question is, basically, we want to know, is she surprised? So how can we turn that into a probability question? Usually this will be given to you. What's the probability it will take 23 or more boxes to get a full set of 5 NASCAR collectible cards? All right, so let's see how we can use technology to answer this question. All right, so the first thing you're going to want to do in the state portion is basically state what the question is asking you and how you're going to do that. So notice how the second part of this is just a rewording of the question. We are going to assign numbers to represent different NASCAR drivers found in each box in order to determine the probability that it takes 23 or more boxes to get a full set of 5 NASCAR cards. All right, so how are we going to do that? So you're always going to assign numbers, and the tricky part here is deciding how you're going to assign numbers to represent the probabilities. So in this case, we are going to assign 1 to be Jeff Gordon, 2 to be Dale Earnhardt, 3 to be Tony Stewart, 4 Danica Patrick, and 5 Jimmy Johnson. Because basically, think about this. You have a pile of numbers, and you want to know how many boxes, what's the probability it takes 23 or more boxes to get all 5 cards. Well, I have to then somehow label these cards using numbers. So that's why we use 1 through 5. All right, so then on our calculator, we're going to use a random int 1, 5 to simulate buying 1 box of cereal and looking at which card is inside. All right, so think about how you're going to do this on your graphing calculator. So we're basically counting. We're going to do 1, 5 on our calculator. We're going to keep hitting enter until we get all 5 different numbers. So in this case, we're essentially ignoring repeated numbers because I don't want the same one twice, okay? We're going to count the number of total boxes, but we're going to keep going until we have all 5 different numbers. So how do we write that? Because we want a full set of cards, we're going to keep pressing enter until we get all 5 of the labels from 1 to 5, all right? We're going to record the number of boxes that we had to open. We're going to ignore repeats. So ignoring repeats is saying we want to get numbers 1 through 5, and then we're going to count how many total boxes or how many total times it took us to do that. So how do we do this? In this case, we're going to repeat the simulation 5 times and record the results. Now, since we're doing this experiments until we get the numbers 1 through 5, we're going to see how many boxes we had to open until we get all 5 different numbers. So you would do this on your graphing calculator, and obviously, since everybody's a little bit different, everybody might get a little bit of a different answer. So on your graphing calculator, if this is what you hit enter, and you get 3, 5, 2, 1, 5, 2, 3, 4, okay? In this case, it took us, we did have a 5 right here. Oh, the black number. So 3, 5, 2, 1. The red are the repeated. We ignore those. 4. So we have 1, 2, 3, 4, 5. Took us 9 boxes. Do this again on my graphing calculator. Next time it took 16 boxes. So the black numbers are the non-repeated. So I got 5, 1, 2. Then I started repeating, got a 4, kept on repeating all the way till I got a 3. So this time it took us 16 boxes. Next time it only took me 10. So reds are my repeats. Blacks are the numbers that are the non-repeats. Okay. Rep 4 took me 15 boxes, and Rep 5 took me 22 boxes. Now, when we have larger, more technology than just us sitting over there doing it over and over again, it makes it a lot easier. But this dot plot below shows if we did this, shows the number of boxes if we did 50 repetitions of the simulation. So that's why technology is sometimes a little bit easier. Okay, so this is 50 repetitions. So here, in this case, we only had to buy 5. Okay, in this case, we had to buy like 22. Okay, we had 15 here, 10 boxes here in order to get all 5 different ones. All right, so now what's our conclusion? Okay, so let's think about this. We never had to buy, if you look at the previous page, even on this one right here, 22 was our highest. We never had to buy more than 22 boxes to get the full set of NASCAR drivers in 50 repetitions. So our estimate of the probability that it takes 23 or more boxes to get a full set is about 0. The NASCAR fans should be surprised, all right? Because if you look back at our graph right here, what's the probability that it took 23 or more boxes? Well, in 50 repetitions, that probability is 0, right? Because it didn't even take us 23 boxes to get all 5. So something was messed up in hers. All right, so let's take a look at another example. So this example is going to estimate probability. So suppose I want to choose a simple random sample of size 6 from a group of 60 seniors and 30 juniors. To do this, I write each person's name on an equally sized piece of paper, mix them up in a large grocery bag. Just as I'm about to select the first name, a thoughtful student suggests that I should stratify by class. So you agree, and we decide it would be appropriate to select 4 seniors and 2 juniors. However, since I already mixed up the names, I don't want to have them separate again. Instead, I will select names one at a time from the bag until I get 4 seniors and 2 juniors. This means, however, that I may need to select more than 6 names, all right, because I may take more than 2 juniors, so I might get junior, 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 junior before I get the 4 seniors. So we're going to design and carry out a simulation using our random integer table in this case to estimate the probability that you have to draw 8 or more names to get 4 seniors and 2 juniors. So this one's a little bit trickier. So kind of think about this in your head for a second before we move on. All right, so here's the tricky part in this one. The tricky part in this one is that I have 60 seniors and 30 juniors. So what do I do with that number? And then what do I do with the fact that I have 8 or more names to get 4 seniors and 2 juniors? So basically what we have to do is we have to assign numbers to the 60 seniors and the 30 juniors, basically throw those numbers in a hat and use a random integer table to select those numbers. Once I've selected those numbers, I'm going to keep selecting them until I have 4 seniors and 2 juniors and see if it takes 8 or more names to get those 4 seniors and those 2 juniors. All right, so let's see what that looks like. So that's the tricky part here. Once again, remember the state is basically just putting the question into a sentence form. So we're assigning numbers to senior and junior names to find the probability of drawing 8 or more names in order to get 4 seniors and 2 juniors, restating the question. Here's the tricky part. Think about throwing the names in a hat and basically assigning numbers to the people that you have. So in this case, we're going to assign 01 to 60 to seniors because there's 60 seniors, and 61 to 90 to be juniors because there's 30 juniors. So I'm just taking my seniors and my juniors and assigning numbers to them. Now notice, think about groups of 2 numbers. You can go 0, 1, all the way up to 99. Okay, and after that, they basically, start doing like 3-digit numbers. So the 2-digit numbers that are not included in this set is 91 to 00. All right, so we're omitting 91 to 00 and repeated numbers. Why are we ignoring repeated numbers? Because we want 4 different seniors and 2 different juniors. So when we have a repeated number, we already chosen that person. We don't want to choose them again. All right, we're doing this without replacement. So how do we do this? We use random int tables starting at line 101. So we're telling the person where to start. Because we've assigned 2 digits to the juniors and the seniors, we're reading every 2 digits until 4 seniors and 2 juniors are picked. We're going to count the total number of names drawn, and we're ignoring repeats. So basically, we're just looking at numbers. We're seeing getting 4 juniors, 4 seniors, and 2 juniors, and counting how many numbers we had to pick until we got 4 juniors, 4 seniors, and 2 juniors. Keep saying that correctly. Haha. All right, so let's take a look at the next slide for the do and conclude. All right, so if you think about this, looking at a number table, so 19 is a senior, 22 is a senior, 39 is a senior, and 50 is a senior. Boom. 34 is a senior, 5 is a senior, 75 is a junior, 62 is a junior. Okay. In this trial, it took exactly 8 selections to get at least 4 seniors. So we have 19, 22, 39, and 50. Now, even though these weren't repeat seniors, we didn't want these 2 guys. We only wanted the first 4 seniors, so we're kind of ignoring them because we had to keep going until we got 2 juniors. So 1, 2 juniors. All right, now, we only did this one time. A calculator or some technology can do 50 trials. So this means it took 6 trials to get exactly 4 seniors and 2 juniors, 7 trials to get 4 seniors and 2 juniors, 8 trials to get 4 seniors, 2 juniors, so on and so forth. Okay. So we want to know what's the probability that it took 8 or more to get exactly 4 seniors and 2 juniors. So if we were to count this up, 25 of the 50 trials, so physically I just counted these, 25 out of the 50 required 8 or more selections to get 4 seniors and 2 juniors. I can't say that correctly. All right, so the probability that it takes 8 or more is about 50%. So 50% it took less than 8 and 50% took 8 or more. So that was just using the simulation to estimate that probability. Okay, so last one. At the annual picnic, 18 students in a mathematics or statistics department at a university decided to play a softball game. 12 of the 18 students are math majors, 6 are stat minors. To divide into 2 teams of 9, one of the professors put all the players' names into a hat and drew 9 players to form one team, with the remaining 9 players forming the other team. The players were surprised when one team was made up entirely of math majors. Is it possible that the names weren't adequately mixed in the hat, or could this have happened by chance? So design and carry out a simulation to answer this question. All right, so very similar to the last question. So think about this before you take a look at the answer. So state, once again, you're just restating what the question's asking you. What's the probability that there will be one team with all math majors when randomly assigning 12 math majors and 6 stats majors to 2 teams of 9? So we want to know, how are we going to end up with all math majors, 9 math majors on one team? How can we do this? Using 18. All right, so how can we plan to do this? So we're going to take 18 equally sized slips of paper, label 12 of them M for math majors and 6 of them S to represent the stats majors. We're going to shuffle the papers well, divide them into 2 piles of 9, record whether or not one of the teams is made entirely of math majors. All right, and we're going to do this a couple times. Now, you could obviously do this using numbers too, using a simulation. That's totally fine. So here's an example of one trial. Team A ended up with 8 math majors. So this was just taking the 18 slips of paper and randomly dividing them into 2 groups of 9. So this one had 8 math majors. This one had 4 math majors. In this trial, neither team was made up entirely of math majors. If we did this 29 additional times, there was only one trial where an entire team was made up of math majors. So then you want to come up with your conclusion from that. So since only one trial in 30 resulted in a team with all majors, the probability of getting an entire team was about 0.033. Because getting a team of math majors is very unlikely to happen by chance alone, we have convincing evidence that the names were not shuffled very well in the hat. So is it possible that the names weren't adequately mixed, or could this happen by chance? In this case, the conclusion you wanted to conclude is whether or not it happened by chance alone.